In this video, we consider the example of the force method with a frame. I have constructed an example here where we have a frame consisting of two members, both of length L, and we have joints A, B, and C. At joint A, we have complete fixity of the beam at A. We also have moment restraint at C. We also have restraint in the vertical direction at C, but it is free to move in the X direction at C. We also have an applied moment M at joint B. We've also established here that the E and I for each of the frame members is constant, and our objective is to find the reactions at A and C. And we're going to do this by using the force method. So then, the solution proceeds as follows. First, we need to find the degree of indeterminacy so that we can decide how many redundants we need to use in our force method. And so what I have done here is I have drawn a picture of our frame with all of the unknown reactions indicated. We have a Y reaction at C, a moment reaction at C, and we have a shear, axial force, and moment at A. And I have numbered those redundants. Well, actually they're not redundants yet. They're just reactions in this case. And so the number of pieces in our free body diagram is 1. We have 3 equations of equilibrium in a 2D problem. And so 3 times n is 3. We have 3 equations. And we have r, which is 5. That's the number of reactions. And since r is greater than 3n, this structure is indeterminate. And so if we take r minus 3 times n, we get 2, and that lets us know that we have a second degree indeterminate structure. Knowing that our structure is second degree indeterminate, we need to choose 2 reactions as redundants. And so we are going to choose reactions 1 and 2 as the redundants. If you recall, in our original numbering of the reactions, reactions 1 and 2 were at joint C. We have the vertical reaction at 1, and we have a moment reaction at degree of freedom 2. Once our redundants are chosen, we can draw the primary structure. The primary structure is the structure where we have drawn the frame and we have removed those reactions 1 and 2, and we have put the original loading of just the moment loading at joint B. We have applied that to the structure, and we have imagined the deflected shape of the structure. This beam or column here, AB, has some curvature to it due to flexure caused by this applied moment M, whereas the beam from B to C has no loads applied to it, and it just rigidly rotates due to this applied moment M. This is our primary structure, and at each of those redundant locations, we have indicated the displacements that occur on the primary structure due to the applied moment M. And so you see there is this vertical displacement of C, which we are calling delta P1, and there is a rotation of joint C that we are calling delta P2. Now, we're using the delta symbol, but that is indeed a rotation, and it is the rotation of the end C with respect to a horizontal line. It is important that you note here that the end at C rotates the same as the joint B. Because this bar BC has rotated rigidly, the same rotation that happens here is the same rotation that happens up there. Hence, B rotates like the end of a cantilever with applied end moment. So we have an applied end moment. It's been applied at the end of this cantilever from A to B. And if we were to look on the inside cover of the textbook, we would find that that rotation at B is equal to ml over EI. Well, as we've indicated here that we should note, the rotation at B is going to be the same as the rotation over here. And so using that inside cover of our text for the rotation at the end of a cantilever with an end moment applied to it, we have delta P2 then is equal to ml over EI. For small rotation delta P2 is indeed a small rotation. All of the theory that we are covering in this course is for small rotations. And so for the case of small rotation delta P2, segment BC has a deflection at C of delta P1 right here, and it is equal to this radial distance L times the angle that BC has rotated through. And that's just an example of using the arc length formula, which is to say that the radius L times the angle of rotation is equal to the arc length change. And for very, very small angles, it's just this vertical displacement delta P1. And so if we take L and we multiply it times delta P2, we get ml squared over EI for the displacement delta P1. After analyzing the primary structure, we are ready to consider our redundant structures. Let's first draw the redundant structure for the redundant at 1. And so we have the structure. We have the applied redundant reaction at 1. We now must consider the displacements at each of the redundant locations due to this R1 force acting on the structure. And so we have that this end is going to move upwards, and we call that delta 1, 1. That is the displacement at 1 due to the redundant at 1. And we also see that this end up here has rotated from its original horizontal configuration, and we call this delta 2, 1, which is the displacement at position 2 due to the redundant acting at 1. And so in general we have that delta ij is equal to the displacement at I due to the redundant at j. And we can write that displacement delta ij as Fij times Rj, where Fij is the flexibility coefficient, and it is Fij, it's equal to the displacement at position I due to a unit load at redundant j. And we will make use of that often as we use the force method. Now, as we consider this redundant structure 1, we must find F11 and F21. And we can write our displacements in terms of those flexibility coefficients. We have delta 1, 1 equal to F11 R1, and we have delta 2, 1 equal to F21 R1. First, let's try and find F11. In order to do that, we need to consider applying loads to our structure so that we can apply the principle of virtual work. Now, when we find F11, really what we're doing is we're saying that we want to find the displacement at I due to a unit load at the redundant J. And so we have the moment diagram due to the unit loading right here, and we have the unit load in the direction of displacement that we want to find. And so we put a unit load here. And so we can think of this as the real loading causing the real displacement, and this as the unit load in the direction that we want to find the displacement. And it is the load that is riding along as we load it with this unit load 1. Well, what we've done is we've constructed a moment diagram for this real situation where we have a unit load here. And you can see that for this upper beam here, we're going to have a linear moment variation. This is not too difficult to understand or to realize because we can see that this unit load is going to be causing 0 moment where it's applied. But by the time we get over here, the internal moment should be 1 times the length of the member. And so that's 1 times L, and so the moment has to be L at this spot. Well, in order for joint equilibrium to happen here, we need for the corresponding moment down in this member to be equal to the moment right here. So this moment has to equal that moment for joint equilibrium, so that moment is also L. That means that we have an applied moment inside the beam here of magnitude L, and there is no shears along here, so it must stay constant until we get down to the bottom. We still have a constant value of L, and it is constant throughout that vertical member. The very same loading is happening over here, and so we get the same moment diagram. Now, Fij is equal to m sub I, the moment at location, or I should say the moment caused by a unit load at I, and J, the moment caused by a unit load at J. That integral over EI times dx is what we need to find to get the flexibility coefficient F11. And in order to do that, we're going to use the integral tables of MM that are provided on the inside front cover of your textbook. So in this case, to get F11, we're going to consider these two rectangles, and using the integral tables, we see that this should be L times L times L over EI for these rectangles. And then we have for the triangles, we have the integral of those as 1/3 L times L times L over EI, and that simplifies to 4/3 L cubed over EI. Next, we need to find the flexibility coefficient F21. This is the case for which we want to find the displacement at 2 due to a unit load at 1. So we're wanting to find a displacement here, and this is at the location where we have the rotation at node C of our original structure. And here is the unit load being applied. So the unit load is what is going to be causing this rotation here at position number 2. So we have to consider these two loadings on our structure and construct the moment diagrams for each case. We already had this situation when we did F11, and so we know it looks like this. Then if we look at this one here, we have an applied moment of magnitude 1. It causes a moment of 1 at the end. Over here, if we had some moments about this point, and we found the internal moment here, we would find that it must be equal and opposite to that, and so we just have a constant moment of 1 in here. Again, due to joint equilibrium, This value here must be equal to that one, so we know we have a value of 1 for the moment here. And also if we sum moments about the whole, well, about point A, which is right here, due to this applied moment, this moment right here at this location must be 1 also. So it's not too difficult to tell by statics that there must be a constant moment of 1 for this column A, B also. Notice that this capital M moment diagram is for the real situation, which is loaded by this unit load. This is where the unit load is loading the structure, and we also have the virtual lowercase moment. This is where we want to know the displacement, and this is why we have applied a load in the direction of that displacement that we're interested in. And since it is a rotation, our unit load in that direction is a unit moment. In order to get F21, we of course use the inside front cover of our textbook again, and we see that for these two rectangles, our moment would be L times 1 times L over EI. And for this triangle and this rectangle, we have 1/2 L times 1 times L over EI. And this term here, adding those up, equals 3/2 L squared over EI. Next, we need to apply redundant reaction R2 to the structure. So if we draw our structure and we apply redundant reaction R2, we're going to get a deflected shape, and we're going to get a displacement at the end, a vertical displacement, which we can call delta 1, 2, and that is the displacement at redundant 1 due to the redundant applied at 2. And we also are going to have that our position C is going to have a rotation with respect to its original horizontal position, and so we have a rotation of that end of delta 2, 2, and that is the displacement at 2 due to the redundant at 2. And so this is our redundant structure number 2 drawing. In this situation, we must find F12 and F22. This is so that we can find our expressions for delta 1, 2, which is equal to F12 times R2, and delta 2, 2, which is equal to F22 times R2. First, we will find our flexibility coefficient F12. In order to do that, we need to imagine that we have applied our redundant, or I should say our unit load at position 2, and we have applied a unit load in the direction of the displacement that we want to find. So remember now, this is the flexibility coefficient for the displacement at 1, hence we are drawing our unit load in the direction of redundant 1, and it is due to the unit load applied at redundant 2, which is here. We can construct our moment diagrams similar to the way that we did in some of the previous slides, and we can then write our expression for F12 using our integral tables. And so firstly, we have our two rectangles here. We have 1 times L over EI plus a rectangle and a triangle, which is going to be 1/2 of 1 times L over EI. After doing the algebra, we get 3/2 L squared over EI. Now, we can see if we look back we can see that this F12 is exactly the same as F21 that we found previously. And this should not be a surprise to us because we know in general that Fij equals Fji. Our flexibility matrix is going to be symmetric. We didn't really have to find this all over again, but this does demonstrate that things are working as they should. We also need to find F22. Hence, we need to apply a unit load at the position where we want to find our displacement, which is in the direction of displacement 2, which is a rotation displacement. And we want to find it for the situation where we have applied a unit load at position 2. And so we have these two moment diagrams that result due to these loadings. For this situation, we then can write that F22 is equal to 1 times L over EI. That's for these two rectangles. And then for the upper rectangles, we have 1 times L over EI. And after simplifying this expression, we finally get that F22 is equal to 2L over EI.